Hello and welcome to MVP Days. My name is Alessandro Gonçalves and I would like to talk about storage performance and how to look under the hood. We have 30 minutes and definitely it's not enough time to cover everything, but I hope to show some little tips that may help you uncover some performance issues with storage. This is a diagram of a generic I/O subsystem. You see many layers, and what we need to understand is that an I/O will go through all those layers, and each layer will add its own attribute and properties. But basically, I/O is just a memory transfer and is basically packet driven. It means it's independent from each other. We may hear about the synchronous and asynchronous I/O, interleaved I/O, but those are properties of the application, how the application handles I/O, how it shares resources, how it does thread synchronization. All those things are controlling how the application was coded. But the I/O itself is just a memory transfer. And here's you can see about on Windows, if I just put names on the some Windows drivers and components, and we see one important one, Starport.c, that we're going to talk today, is right down at the bottom of the stack. And that's very important because if we can observe the IOs going through that layer and mark when it begins and ends on that layer, we can make sure that the latencies are coming either from the layers up in the stack or down on the physical layer, on the hardware layer. And also, one other thing that we need to look at is where are we getting our data? So every single performance monitor object comes from a particular layer, and we need to know where in the stack it is. So we understand a little bit more how many layers are adding to the number that we see if we're talking about the I/O performance. So one thing to understand about I/O is we need to understand a lot of it. So we need to understand how big it is, where the locality, which is the pattern, how many parallel commands are issuing, are we using caching or not using cache, what type of physical device we're connecting to, how we're connecting to those physical devices. Everything will add up to understand if we are performing the way we should and how we troubleshoot that. A Starport trace, basically, it is looking at every single IO going through that particular place on the stack, which we call Starport trace or Starport.sys. It has been present since Windows Server 2008, but people have not caught up sometimes on it. It's very powerful and it's very easy to see IO pattern and how we can group those IOs. Right now, if you look at 2019, we have those latency buckets. Basically, they take a Starport measurement and just display in an easy fashion for us. So let's do some demos while we are here, since we don't have that much time. I'm going to try to show you some disk speed and some performance monitor, some XPerf, so we have a lot of things to cover. So let's start with a perfmon and our IO or Starport tracing. So manually you can create a event trace session. what we call, here we call Starport. Let me just delete this one. And let's create another one. So we go. And here you're going to see all the providers that we can create event traces. There are lots of those, you can see. It's very nice from Windows to have these ETW providers where we can get deeper and deeper information about basically anything. So let's find Microsoft Windows Store, Storage, Starport. We're getting close. Storage space here, Microsoft Starport. Here it is. So you see that we have lots of Microsoft storage spaces. So if we need to get deep, we can. Obviously, we need symbols. We need tools to open the ETL. Luckily, Starport lets us. And also, we need to know what we want to trace. So instead of getting several keywords, what we want is basically a I/O performance, which will give us the latency below Starport. Check OK. And next, you select where you want to save. Save at perf logs. Next, and you finish. I'm going to say that to stop it. What I normally do here, it is to set a stop condition to a max file size, 300 megabytes. Depending on what you do, 300 megabytes would be fine, and set that to a circular log fashion. So let's apply, and we can set that to circular log. Another thing is look at the trace buffers, increase the trace buffers, mainly if you're doing any kind of benchmarking, because you're going to lose. So set those buffers to 1024. Should be plenty. And basically we are ready to start collecting. Once you collect a Starport and you reproduce what you want, it will create your ETL file. On the perf logs we have here Starport, and this ETL file you can technically open with your event viewer, but that will show you only some. So this is the Starport that we have by default inside the Windows 2019. So application service and logs, Microsoft. You have Microsoft's, and here you have the 505 event. You can see lots of information here. The 505 event is our I/O latency buckets. So 2016, 2019 does have that. So you can see on that capture how many, what's the I/O count, and which one in each bucket. So the first bucket, which is below 256 microseconds, we have most of our. So it means that we are very good here, no problems. So let's total I/O count, everything here. But also we could open that ETL, which I open already for us. And we have different events. So instead of having the 505, we have 201 and 200. which is basically how long each I/O took. So what's in the Windows event viewer by default is just a bucket, so it's aggregation. And here is each one I/O going through. We can see the command that it did and the request duration in hundreds of nanoseconds. So it's very, very powerful indeed. So what you can do is to transform this ETL into a CSV file. For this, you need the xperf utility and just xperf -i and the xperf let me take this one here. And if you can do xperf I Starport ETL output to test one CSV, for instance, and you basically create a ETL file and you convert ETL to CSV. So in this case, what you have, you can open now in an Excel format. I basically clean up that and just leave the top tier with the process, thread ID, but what I'm looking for is basically the request duration in hundreds of nanoseconds, the command, these are SCSI commands. In this case, we have read and write when we can select one by one. So let's see on writes and the port, right? So we can see what's the, so you could see that here I'm creating lots of 4K. So basically it is a disk speed scenario to a single device. And then we can create a graph. You just get the timestamp and the request duration. And you can create a graph, a scatter graph. I like the scatter graph. It shows you a pattern here. You see here, like your latency going up and down. And you have two bands of latency, which is interesting here. Most likely will be different NUMA nodes that you're getting latencies. So just remember, those are hundreds of nanoseconds. So 2,000 hundreds of nanoseconds is basically 20 microseconds there, right? So that's what we need to take care. So that's, in a nutshell, a Starport logging. So you create a log, you transform ETL to CSV, and you can work on Excel. So if you want, you can change, for instance, here, I can change my port to another drive, to another NVMe drive, and see how it's going to behave. And you can insert a graph. And you see that the graph is completely different pattern. So what normally look here for are for patterns of increase in latency. So when I see these spikes right at the same time frame, I normally going to see some kind of queuing and timeout or resets. So either coming from somewhere, right, below the stack, or this also could mean that I'm issuing a lot of I/O at the same time. Think about if we're not doing a benchmarking. Think about a high-end database doing lots of checkpoints in in the same interval. So look, if you look how it is in this type of scenario, right? And it is reads. If you let's see if the read, so it was right. So let's see if the reads follow the same pattern. They technically do. So I could say that either I'm queuing somewhere, so I need to know where I'm queuing. So we can see, so it could be a queuing or a burst of I/O that increases the queuing at the same time. So let's see how we created that. So let me go back and let's do some experiments with disk speed. So let me show you so I have here clean CPU, 64 LPs. Let's do a regular disk speed here. The interesting fact about those two disks, they are going to two different devices, but one I'm doing kind of direct access, so I'm bypassing lots of my I/O stack layers. So volume manager, partition manager, file system, I'm not passing through those. I'm going straight to Starport and controller. And this one to another device, I'm doing the regular I/O path, file system, volume manager, partition manager, and so on and so forth. They are two Optane devices, actually. And I also notice that I point to different, I set manually the thread affinity. So I am setting this. So technically what I did, I split the threads on NUMA nodes 0 and 1. So let's see the results here. Let's get total and total. Total I/O. So here we have 397,000 IOPS. Here we have 500,000 IOPS. Interesting, right? So direct access, way faster, more efficient. I don't know. That's depends on how you see. I can say that this is a more efficient way because we have less layers to go through, and my latencies they are different here on direct access. You see here on the bottom threads, they are very close together, so very little variance. But when the file system access, all threads are very the same, so there's very little variance. So there are two things. One, this is a kind of a NUMA effect. So this device is on NUMA 1, and those threads are pinned to NUMA 1. So NUMA node 1. So that's why they are more performatic, and they have same quality of service, let's call it that. And on NUMA node 0, they are more spread around. So even though we have one that they have better performance, but the own quality of service, you'd like to see something, more predictable. On the file system side, yeah, you see that's actually more predictable, but your latency is around 80 microseconds. And here we go from 654 microseconds to 98 microseconds. So a big effect on how NUMA also will deal with that. Another point if you look at is here, our CPU speed. So this variance also meaning that probably I'm on the performance profile that is not high performance, on a power profile that's not. So we can do a power CFG and list and see which one we have active. Actually, right now I'm on power saver. So let's change to this guy, to high performance. And we see that our speed also, our base speed, 256, so our current speed is 259, and so our current speed is closer there. So let's run again and let's see how we're doing. So 431, so you see the file system is a little bit better now, because when we're going through file system. So this just shows you some of difference that we have, or some basic sets can affect how your top performance is. So here we went from 80 microseconds to 74 microseconds. And here we stayed almost the same, but a little bit more punch per thread. So simple testing, power savings, so your BIOS settings, your operating system power profile makes a lot of sense. So I mentioned that Starport trace, and that Starport trace I took when I was achieving the max queue per device at the Starport. So when I say device, it's physical device. So if you have on traditional storage multipathing or RAIDs, that's multiple paths, right? So each one of the devices would, oops, wrong. So actually 255 is the size of the queue. Actually we have 8 threads, so we need 32 outstanding comments per thread. Let's do the same here. 32 outstanding comments per thread. So what happened here is basically, let's go back to our Excel, which I think I closed. Did I? I guess I closed. Well, remember that when I mentioned that the Excel on that Starport trace, we had a high peaks of latency. So you see that we went down. Our average latency went up. See here some actually 1 millisecond. So really really interesting here, right? Because we are forcing the limit of the Starport path. In this case, let's open the do this. So here, this is the Starport tracing for where we have the file system. So they obtain with the full path through the file system to NTFS. So NTFS actually receives the queue full from Starport and stops delivering from time to time. So that's why we see those big spikes of I/O and I/O latency. Those are really, really big bursts. And if we change here to the obtain where we did direct access, so without passing the file system direct to Starport, we see that it's completely different behavior here. It's more scattered. So technically what happens is we still have the spikes, but they are more far apart. And this is just for when the Starport it's completely full, so it cannot accept anymore. So we have retried IOs. And when we have a file system, the file system has a understanding with the lower layers that okay, I have a queue that is full, and then I stop sending to that queue, but I continue receiving IO. So there is a kind of a smooth training over there. So that's kind of the Starport. So what I look for is those trends and what type of command, the size, so I can have all those types of information, right? So the last point, so we did the queue, is the industry performance analysis. So in this performance analysis, there are several types of things that you can trace. You can trace big, give me all this IO with file and CPU, or you can trace small, like a Starport or a particular function. You have all that. And when we talk about storage space direct, it's always good to understand that we have a storage and network component for the IO path, right? So we have the intranode replication, we have SMB over DMA, so we need to know how much time I'm spending on the client, how much time I'm spending on the SMB server, on Starport, on block filter driver. So all those come into place. And here we're talking about the host part. So when you take a XPerf trace, and you can look with the Windows Performance Analyzer, which is a really powerful tool. So here I have my disk utilization. So you see our local disks, our remote disks per storage space, right? So this is an actual trace from a S2D cluster. I can do several things, but the basic here is you can aggregate for everything that is left of the golden bar. So here I'm aggregating first by disk, but I could aggregate by process. So if I just move, so now I have process. And here, if you're talking about only IO, we have 2 points here. One is disk service time, which is our Starport, and the other one is IO time. So it's the full time that IO took on the whole layers. So you can, split and okay, disk 18, what type of IO read and write. So we have this and how much was spent. This, and we can change here. So for instead of sum, we can do average. So there are a lot of ways to show. Other you can see offsets of disks, so see the pattern if it's sequential or not. Throughput, you can leverage throughput by disk or by process. Here, it's an interesting one. So since we're dealing with Storage Space Direct, we can deal with functions, right? So how long a function has been, so what's the timeline of on that function? So for instance, here we have the Intel NVMe driver, and we're spending a lot of I/O completion time, of course, and this. Uh, and Starport, we have the Mellanox. So how Mellanox, here I don't have symbols for the function Mellanox, but I can see a split of how many calls for each function I did. Another one that I like to do is our flame graph, which I can span the stack and see, what's the weight for each call, each function. So there are a lot of things to investigate if you're looking for trends, how long a function spend on each time. I could spend hours just talking about that. Unfortunately, I don't have that much time. So most likely, if you guys are interested, I can put something together. But you can see that I can go down and let's pick one and then just go down and see how long did it take on each one. So, and basically what I need to follow is the weight and the count here. So every time I spend here, so this function, this start thread is the one that has the most. Of course, we're starting thread. So if I expand that below this, we have two split ones here, right? See the top. So if I expand this, I can go on and see. So here we're calling star VSP, and if you see here, Mellanox have only called two. So this particular function, right? So and it goes on and on. So we can actually go and see how much time I spend on each point of the stack. So that's the basically assumption that I want to show you guys. So understanding this path, you have the understanding of the where I should concentrate, where should I go? Should I go Microsoft? Should I go Mellanox or Intel? So that's basically what I want for you to take a peek. I'll let my slides, and I hope you have more questions. And like I mentioned here, you should practice because it's a very powerful tool, but it takes a long time to master something out of it. So thank you for your time. A little quote here, and I hope to engage with you guys on the Slack channel, and if you go to Ignite, I see you there. Thank you very much.